Hello, in this video I'm going to show you briefly how to calculate the value for Pearsons correlation and a p-value for a t-test. So in this first spreadsheet, as you can see, I have my data laid out. So the Pearsons correlation is where you're looking at a correlational relationship between two variables, and in this case we've got paired data where we've taken the heart rate of a person and the systolic blood pressure of a person, and we've so these are measures done at the same time, two different measures, and then we do that over time, and we see, or we want to see if there's any relationship between the heart rate and the systolic blood pressure. So to work out if there's a correlation here, we're just going to place the cursor in a box there. We're going to go up to the functions. I've already got it there because it's on my most recently used, but if it's not there, we're going to get into the statistical option, and these are all in alphabetical order down to Pearsons, which I've just gone past. There we go. Click on that. It'll then bring up the array box. So array 1, it's asking you for the first set of data. Go back over the data. Hold the left click down on the mouse, and let's pop the data into that box. Second array, same deal here, pop that into there and hit the OK button, and we've got a number pops out at 0.969. We can actually reduce that down a little bit, so that's pretty close to 1. So we'd say that's an extremely strong positive correlation, and the way we'd represent that would be R equals 0.97 for writing that up into an analysis in our paper. So it's that simple. We will calculate the other ones in class and discuss the differences there. Now, t-tests are the second one. So t-test is where we want to calculate mean, standard deviation, and the t-test at the end. So to do the mean, it's the same deal. Up into the functions box, we're in the statistical area now. They call it an average in here, so it's going to take that average, and it's taken that data E7 to E13 without me having to tell it. We can do the same for standard deviation. Go down to standard deviation. Now with standard deviation there are a number of options. We want to take standard dev.s, which is for samples, so only a small sample, and we're going to take that one, and it's asking us for the numbers that we want to put in there, so we're just going to pick those numbers there. Make sure you don't pick up the mean as well. Hit the OK button, and that's giving us a standard deviation of 12. We can then do the same for class B, but an easy way of doing that is to just drag those across. So we can now see that we've got, in the first class, we've got a mean of 38, and in the second class a mean of 64, and the standard deviation for the first one is 12, and the standard deviation for the second one is 13. So the dispersion of the data is quite similar, but the means across those two sets of data are quite different. So let's now do the t-test. So going back up to the function button again, the t-test is a little bit more, requires a little bit more data. Here it is here. So to go into the t-test, asking us for the first array, which is that data there. Second array, pop that in. It's asking us for tails, so what we're talking about there are the ends of the distribution. So for our data, we'll say that we're interested in the two tails of the data being included. Oops. So we're going to put 2 in there. You can either put 2 or 1. And then the type of data. So if these were paired numbers, for example, the 50 and the 80 were, say, a pre-test and a post-test for the same student, they would be paired data. So in this case, it's not paired data, so we're not going to take the option 1 here. We can then look at option 2, equal variance. So the way to think about this is the data highly dispersed? And if we look at the standard deviations, they're fairly similar. So we'd probably say they're fairly equal in variance. If there was a massive difference, if there was big differences in the standard deviation, we might take option 3 there, but we'll take option 2, and option 2 is probably fine. It doesn't actually make a lot of difference on this particular set of data, so I'm going to put option 2 in there. And we come up with a number, 0.0018, and if we're thinking about what we looked at in the other video where I said a cutoff of 0.05 could be significant in a school science context, then that difference that we've got there is quite highly significant. And as I explained in the other video, this is because the t-test takes into account the absolute difference between the means, and there's quite a big difference between those two means. And it also takes into consideration the standard deviation, the dispersion of that data, and they're quite tightly dispersed. There's not a lot of dispersion in that data set. So for that reason, the t-test has come up and said that there is a highly significant difference in that data. Now, once again, to represent that in a paper that a student might write, we'd write it up something like that, that the p-value for this particular comparison of means is that p equals 0.008, and if our predetermined cutoff was p less than 0.05, we would then say that that p-value is statistically significant, and therefore the difference between the two means is statistically significant. And it's as simple as that in terms of calculating these statistics.